Cool. Okay, the way we do that, pause if you want to look at that. The way we do that is via a determinant. So we call them Slater determinants. And I'm going to just give you an example. So if you don't know what a determinant is, Google it. But it's a way of, you learn a lot about determinants and when you're doing matrix stuff. But if I have 6, 4, and 3, 2, and I take the determinant of this, you may have learned this in Calc 3, Calc 2 maybe, definitely in linear algebra. If you take the determinant of this, you get, so you do cross multiplication. So 6 times 2, which is 18, good God, 12 minus, oh wait, no, I did that wrong. Yeah, sorry. So 6 times 2 is, this one doesn't, this is not a good example because it's 12 and it equals 0. 2, 4, there we go. Of course, the example I pull out is the one that doesn't work. Determinants. To determine the determinant, you take 6 times 4, which is 24, minus 2 times 3. Oh, goodness. I've lost all credibility, which is equal to 18. If you exchange these two, 3, 4, 6, 2, you get cross multiply 6 minus 24 equals minus 18. Go team. Determinants. If you take your psi 1 with one configuration, and then so electron up and electron up, or 1, 2, psi 2, 1, and then you psi 2, 1, psi 2, or 1, 2, and then you exchange those just like I just did here, and you get a negative sign out upon the exchange. When after taking the determinant, you have verified. Psi is good. What does it mean for psi to be good? It's continuous, it is square integrable, it satisfies the boundary conditions, it satisfies H psi equals E psi, and gives you N, L, and M sub L values, but it also, with this extra check, gives you M sub S values. It tells you that you have a good wave function that follows the Pauli principle. Cool? That's the Pauli exclusion principle. It's that, well, the Pauli principle, and then the subset of that is the exclusion principle, which says the result of once you have a wave function. The determinant was just an example. In the 9th edition, there is a very long example about the determinants. Atkins thought that was too much. He took it out for the 11th edition. I'll post a picture of the 9th edition, so 11th edition nerds, y'all can see it. But that's why. It's a way to check that your wave function is a good one. But, oh goodness, that's too close. How do we know that these are the ones that give us the only satisfied wave function, that this happens? You take the determinant of this, and then, so of this with the flipped option. And then you see if you get a negative sign. You don't with this one or this one. You do with this one and this one. Cool. So the result of that is that no more than 2 electrons may occupy any given orbital. And if 2 do occupy one orbital, then these spins must be paired. And that pairing comes from the fact that you've got spin plus half, spin minus a half. And so if you look at figure 8b.3 or 9.18, you can see the spin cone shape that comes out of it. So that's where you have the restriction that you have to have net spin be 0 in a paired orbital. Cool. Okay, I hope that helps. The Pauli exclusion principle, again, it is a condition of the wave function needing to be negative upon the exchange, and it's a result, and the exclusion principle is a result of the Pauli principle. Pauli principle is this: need a negative sign. Exclusion means if you need a negative sign, the only way to get that is spin up and spin down. Go team.